All right, okay. So, welcome to the machine learning course. My name is Morris. I'm from the Jülich Supercomputing Center. That's one of the institutes of the Jülich Forschungszentrum in Germany, not far away from here actually, close to Aachen. But I'm also a professor at the University of Iceland. The reason for that is that we have a national lab in Jülich, which means largely there's no big university with us, like here the University of Ghent. Instead, we have collaborations with many universities. So we have professors in Regensburg, actually there's one in Leuven, and many others around in Germany, but also across, different European states. And I happen to be in Iceland teaching high-performance computing, cloud computing, and big data, but also the intersection of statistical data mining and machine learning. Hence, this course that you see today is basically oriented towards machine learning beginners on the one hand, and also parallel computing beginners on the other hand. Right? We have here a cross between two different fields in order to speed up data analysis for big data, and we will see how that actually is reflected in the different algorithms we pick. Right? Machine learning is a very huge topic, so I could stand here teaching lectures and lectures that I do at the university, which is basically taking hours after hours. Hence, here I pick specifically here and there topics out of all of these lectures in order to get the messages across that we have here in particular topics. So still, this is not really a full course on machine learning, right? So when you consider to work in this field, then basically you have you still should basically attend really a machine learning workshop or lecture series. So we start with lecture 1, but before I go into the lecture material in itself, we have basically 6 lectures we will focus on in the next 2 days. And we start today with the machine learning fundamentals, where we really have any precondition, anything we know in machine learning. It really starts from scratch, using some flowers for getting some specific topics across, like linear decision boundaries and so forth. So there's also not very much parallel computing, so you just want to understand what means learning from data in a very informal way. Right? When you now learn from a machine learning book, typically you basically get the book and the first 60, 70 pages are just math. Right? So we start with an informal way today, but not leaving out the math. It will coming back to us actually when we talk here more and more about some formalized way how you structure machine learning. But before we do this, the idea of this tutorial really is also being applied, which means you should have your hands on the machines that you have here in Ghent and do some real algorithm. Hence, before we continue, let's say, with the machine learning fundamentals and put them in a formalist way more here in the later parts, we start with a very practical lecture, so to speak, on clustering. Clustering is basically more from the field of data mining, so there's not so much learning if you want, but it's a very nice way of understanding first what it really means to perform data analysis. So we will have here basically some different clustering algorithms like k-means, k-median, but the hands-on will be really based on DB-scan, which is a very interesting algorithm that we will look at in serial, like you will find in MATLAB or R. R is another language for data science where I teach in. So there are different serial languages which doesn't scale for big data. And for this we need the parallel computing, the parallel clusters that you have here in Ghent and also in Leuven, GPUs and so on, and here everywhere in the BSc context. And we'll basically have a short introduction also to parallel computing. We'll check that everybody of you understands what a batch script is, how to submit a batch script, and basically how to log it into the cluster and using it for data analysis. And then we will have basically a real parallel algorithm used, HPC-UGent, an algorithm we developed for clustering that is actually scalable for big data. Of course, here and there, our data sets are not big data because we want to have an interactive session. It's not something like we want to submit the job now, go home, and after 4 hours we come back and meet again. It doesn't make sense, right? So this will be basically the topics of the second lecture, and then we will derive basically lots of aspects from the machine learning fundamentals and put them in a formalized structure. This is actually very much useful, not because just putting it in math the math is still very friendly. It's more given a concrete ground to stand for and to make some assumptions which are basically statistic in nature. Hence, there's a huge overlap also with statistical data mining and statistics. Still, we have here and there, of course, mathematical derivations that we have to look into, like Höfting's inequality, law of large numbers, and so forth. But we keep, again, the mathematics in this tutorial here very much smooth so that we have time to work on clusters. And this really prepares us here with supervised classifications for tomorrow. So today we will do hands-on on clustering. Tomorrow we will do hands-on on classification. However, supervised classification is a very big field, and we prepare that basically in the afternoon today to be ready directly with hands-on all the day tomorrow. So what we will do tomorrow, just as an overview, because it's the first lecture here, and I should also mention the slides are available on the website very soon, so Kenneth is working on it, so that you can always have the slides as well, so there's no need for note-taking or something like this. Also, all the data is open source. It's basically available to you also after the tutorial, so you can play around with it, including all the source codes, right? So all the parallel tools we will see, or libsvm is a tool that we will learn about here, which is a support vector machine in serial. It's also free, open source, so you can play around it. And in fact, libsvm is integrated in R and MATLAB everywhere. It's a de facto standard. And that's maybe a good opportunity to ask, who knows R, maybe? Okay, has used R before? Okay, people have used Riedel before, maybe? It's a GUI for R. Okay, we teach also lots of stuff in Riedel. If you want, just, use library Riedel. You will find some here and there. It's a very nice GUI for data mining. So then, who's using MATLAB, by the way? Okay, yeah, that's also traditional. SAS, by chance? Any SAS statistical tool? Okay, well, one. Interesting. Okay. Right, so these are all serial tools, right? And they're commercial. Some of them are free, like R. But the takeaway message is really that we start here with serial tools, and we'll explore that this takes hell of a lot of time if you have large data sets, right? And some of the kind of analysis jobs we will do and that we will see basically around in lecture 4 and 5, you do this with MATLAB roughly normally about a couple of hours, and we can break this down to 1 minute. And by breaking this down to 1 minute with parallel computing, this speed up means really productivity increased by orders of magnitude. And this is not only when you do and consider training and testing, it's not obvious to you what that means, so we will talk about this actually in the fundamentals now. But when we go to cross-validation, which is a model selection process, which we will then have basically towards the end of the tutorial tomorrow, we will see how we specifically get the model parameters in a systematic way. And there are the most parallelization benefits, where we not only do the validation steps basically in parallel, we can also, let's say, the search phase parallelize that one that we get for good parameters. So all of this will come actually in basically at the end of today, and basically tomorrow much more in depth when we think about support vector machines. Hence today we start with a very, let's say, high-level introduction to the topic and go deeper and deeper and deeper. And therefore I would like to take the chance, who has used machine learning algorithms? Anything, like artificial neural networks? Okay, good. Clustering techniques, hierarchical clustering, k-means, k-median, DB-scan, all right. Anyone in deep learning? Okay, well, deep learning is a very interesting field. We don't talk about in this tutorial, but next week will be a tutorial just based on basically convolutional neural networks, which are a specific part of deep learning. And I will also have there a little bit about LSTMs, which is long short-term memory for time series. Also recurrent neural networks, quite interesting for deep learning today. Just as you for information, so next week we'll continue with the more, let's say, very, very modern algorithms, while here today we have really those that stand the test of time, right? So let's see and go step by step what we will have in the first lecture. So we have to start a little bit with the basics of saying why we want to do that at all. So we want to understand why machine learning is useful. We could think about if you have a formula, why not we just implement a formula and go ahead and implement it. We have some methods in machine learning. You have already heard some of them because of our outline. Classification, clustering is basically the famous examples. There's a regression context also, which is usually more used in statistics, and of course a little bit simpler from the idea. Even if you have multivariate regressions, it's still something where you would consider it gets more difficult. Hence, the learning steps, however, are mostly in the classification and clustering more intense. And then
changing the batteries?
Yeah, sure.
I don't know if it's going to help.
There's some drop-offs.
Yeah, that's great.
Stop drinking so much. Maybe my water. There's a microphone. See. Thank you. Okay, so let's come back. When we do the machine learning basics, my key ideas really go through an application-oriented way, right? So skip the formalism that you have normally in a machine learning book, and have lots of mathematical formulas. We will establish that later. Also, when we come to the algorithms like support vector machines, they have a very nice geometric basically interpretation and math and so forth. But here we keep it simple. Hence, we have the simplest learning model that you can find, which is a perceptron learning model derived from the human brain, neurons actually. And the interesting thing is that these are also the building blocks of neural networks, and in turn also the building blocks of deep learning today. So you see that one of the oldest from Rosenblatt's, in the 50s developed model is still attractive today. Of course, deep learning makes lots of, let's say, modification to the simple learning model, but still that is, let's say, it's so much for the basics, right? It's really fundamentals that you have to know, and it's a very nice model really to think about how learning works, right? We will talk about linear decision boundaries and linear separability, what this term is, because this is, let's say, the basics. However, for some of you that have already used machine learning, it tends to be maybe perhaps a bit boring, hence we have some more, let's say, other parts that we will talk about, like what is really training, what we can do in terms of a systematic process. So when students do, for instance, here and there, some thesis work or some assignments, I structure them according to a systematic process called CRISP. And this is what we will talk about, not so much in the theoretical detail, this is in the appendix, when we have time to talk about it. But basically we have then the chance to go in the systematic process step by step through going to some examples. Then actually machine learning, data mining have different tasks here, like predictive and descriptive tasks. We'll talk about this. And then there are lots of different learning approaches and methods. But you can kind of categorize them in kind of 3 different areas, which is supervised learning, unsupervised learning, and reinforcement learning. And we will talk about this a little bit. However, as you will know basically already from our day outline, today we will focus mostly on unsupervised clustering when the hands-on is, and tomorrow we go much more to the supervised classification. So these terms are all not really obvious to you. We'll see how that materializes when we go through the lecture today. And at the end, we want to a little bit know actually how we can evaluate a model, right? How do we know that our model that we learned from the data is good? There's a term called accuracy or error rates. We will talk about that. So let's start with the really basics, and the motivation why this is now an attractive topic today is probably best explained when you see that is sometimes called the ocean of data, right? There's lots of data, but this is not just basically what we're interested in. Right? The interesting thing for machine learning or for data mining is really get information or insights out of all of this data. So data is fine, we need that, and we will see in a mathematical formula that we need that. And the more, the better in a sense. However, this red fellow, this is what we want to try to achieve with machine learning, to find really the information we are looking for. Either it's a kind of prediction for the future, or it's a description of some behavior, some pattern in a sense. We want to find in the data and extract this useful information. However, the interesting thing is, if you now think it's everywhere in the media, big data analytics, deep learning, and lots of these new big data topics are basically in the media. Many of them are based on traditional data analysis. So especially the fundamentals that I will tell you today are basically really fundamentally based on algorithms that have been existing in the past already, right? But in the past, the problem was often we didn't have the compute power, or we didn't have the memory that we have today in order to get really to big data sets and get them analyzed, right? So here and there, this also kind of motivates the parallelism that we will talk also as part of the course today, so that we really kind of combine machine learning with parallel computing and overcome these memory limits, for instance, by just using more and more and more cores together in a parallel fashion, right? So this is something which is a kind of key motivation in this course. Still, this term I would like to highlight a little bit. Statistical aspects are here and there introduced. We make some probability assumptions on the input space of the data. We will talk about this. So it has some overlaps with statistics and other fields. And this is actually the point by having this diagram, where you think about today people talking about data science or machine learning or data mining. But in a way, like applied statistics, you would see have all an overlap in a sense, somewhere what we these days call data science or data engineering. This is where lots of jobs are today, where you cannot really make a, let's say, very strict boundary of saying, this is machine learning, that is data mining. Right? This is a very hard, let's say, boundary, very soft. You cannot really differentiate between both of them. The same goes with applied statistics topics. Many of them have, let's say, huge overlaps with machine learning, with data mining. However, what a bit the principle is when we look at machine learning, when we try to work with data, is basically these three. And this should be also your kind of recipe. When you now go to practice, you have a job, and someone comes to you, and these are the 3 points you need to check, right? So the first one is always, if you have data, you assume there's some pattern to be detected. That's what we do in machine learning. We try to identify patterns, something in the data. So if someone comes to you in the office and says, here, I have some data, you talk to them and say, what pattern do you think we want to have? So what is a concrete question? What is a concrete idea to analyze this data? You cannot just take data and throw a machine learning algorithm on it and say, okay, this is the outcome. We have by far too many algorithms for that do different things. Right? Still, we need this assumption that there must be somewhere a pattern in the data. Right? It could be, let's say, specific liking of some actor in the movie renting. This is, for instance, just one of the patterns if you do the movie rental. The second aspect is also interesting because if there's a mathematical formula already there for the problem you go to, right? And for instance, when you think about numerical methods and weather forecast, right? That's sometimes questions like they are already established numerical analysis methods, there are formulas that the people have already implemented in the simulation sciences using HPC as well, high performance computing. There's an exact mathematical formula, a physical law, many of them, partial differential equations, you go and implement. It is better accuracy in this sense. Even there's a numerical approximation, has some uncertainties, but you have the formula, you will implement it. There is no need necessarily for machine learning. You can help here, there is a parameter search and looking at some data to help, basically to be, in validation better. But if you have really mathematical formula, normally that's the way to go without using machine learning. Doesn't make sense. I mean, you can still do it, but normally you would say that if there's an established formula, it would be more accurate. And the third one is, of course, the most important of all of them. So if someone comes to you and say, I want to do machine learning, then your first questions basically you ask is, what pattern and what data do you have? Right, and then the interesting aspects begin. Then it goes into the details. So how much data is there really? We will see we need at least a couple of samples to go with. If it comes just with 1, 2, 3 data, let's say elements of your personal, so that's not really going to work. But we will establish that step by step. Maybe an interesting point to point to is here this machine learning aspect, which I like personally because in a way it's very mathematical. As I said, and you have books of it, it's quite interesting to see how very much math is. However, it leaves math many times, right? There's a rule of thumb rule in the game, so you can have just experience. There's no one telling you here and there some specifics, or you kind of invert the math a little bit by just make some assumptions like support vector machines. You will see that don't really exist in one space, but we do the assumptions because they're in sample. So these are interesting things which we'll come to. Also, when it comes to what exactly we would consider a training test set, there's not really a mathematical formula telling you this should be done with this particular algorithm. It actually is an application domain question, and depending on how much data you have. So there's rules of thumb, like take 1/5 for validation. These are the things which is interesting in machine learning, and also is application specific. Hence we come to the next point here, application specific. So here's an example just for you to maybe have a look in the break if you have time, what really application specific means in a certain sense of data analysis. This is a Pangaea data collection, and it's an open data collection that you find is publicly available for every one of you with real scientific data sets. So if you're really interested in the field of working, for instance here in earth science, this is a very interesting data archive to study. And when you look a little bit in all the records and go through it, that we can't now because we don't have the time for it, you will see how complex this subject is. Right? It's not just like the media is now putting the Netflix example, right? Movie renting, we have the kind of different movies watched by many others, so we recommend those movies that are liked by many others. So when you look a little bit in the complex scientific ones into ice, atmosphere, you will see more and more that data analysis can be very challenging. You have time series data, lots of different missing fields. The data is not so beautiful as it always is in the media. So this is a very interesting aspect just to think how really the reality is. However, thinking about here in the course, beginning with the subject, I would recommend to you, perhaps also after this tutorial, with the material you learned today and tomorrow, look at the UCI machine learning repository. So this is a repository with lots of interesting data sets that have been a little bit prepared for beginners in machine learning, and here and there also used as machine learning benchmarks. So you will find data sets like about wine, which are already prepared for support vector machines, a topic we will know tomorrow, or you will find clustering data sets that you can use with the material you learned today with DBScan, for instance. So this is really something where I encourage you, don't let it be with this tutorial. This tutorial can give you just the entry card of data analysis, right? It really is an applied topic, so you have to take real data sets, and here is a good source where you can play around and find also on the internet lots of benchmarking examples so that you can check whether your models in machine learning are good, comparable to others, and what others have maybe done basically to do that. And exactly what we do in this tutorial today is we pick one of the most famous data sets out of this UCI machine learning repository, which is the IRIS data set. Someone heard from that IRIS data set before? So if you buy a book about data mining or about machine learning, you could be, in many cases, very sure there would be an example, around the IRIS data set. And this is about flowers, and this is also something we'll talk today. Before we use this example, let us just look at an overview about the different methods we have, right? And we have basically classification. I will talk now a little bit about it in an informal way, as I saw, not really going very deep into the details, but this is a topic where we have already kind of groups existing. Already some data has certain group items, and in many cases we call that labels. So you have a label to a data set, which means these are the red ones, these are the green ones. Of course, in practice that would mean these are basically those groups that like George Clooney as an actor, and these are the groups that maybe don't like George Clooney in the movies, if there's any dot at all actually in this group, you never know. But the key message to take away is classification then wants to have unseen data. That's what we want to do. We want to create a model that generalizes well in out of sample. These will be terms we'll talk about today, which are very important in machine learning. We want to create a model that generalizes well out of sample, which means when you think a little bit here, you have this already in sample, you know what these groups are, so you learn from them to create a model of just actually thinking about this guy which is out of sample. right? It's not really in our samples, we have not learned from it, but we want to get it right for this dot out of sample. That is the key message what we want to do, basically machine learning classification here at large. So we want to understand if it's a green or red point, right? And we want to get a model, a very simple model as part of this lecture. Now the other part, which brings us a bit more in the unsupervised space, right? If you think about supervised pairs, here's someone guiding us and say, these fellows here, they get a label, they're supervising us and saying, you know, a little bit about what is the data. On this aspect, we have not really a supervisor. Right? There's unsupervised learning in the sense of saying, these are not labeled, they are all noticing dots or data points. Whatever it is, what you call it. But the point is, there is some certain property in the data which makes us think there's again this pattern to be detected. And the pattern that you have here is a similarity measure, for instance, Euclidean distance, right? So it's not a hopeless situation of saying there's nothing in the data, but here you can use the Euclidean distance, for instance, between the different data points to find out their different clusters. Yet nobody's saying that there are different clusters. However, you see human judgment can do it. And what we want to do with machine learning in many cases is to automate this process. Right? It's very easy for us to do this now for the 5 points here. Of course, if you have a real data set with millions of points, you want to automate the process. And hence, that's where these methods become handy. Even if you can do it as a human, in many cases you want to save the time or tedious work and then do by a machine. So then there's also the field of regression, where it's mostly, you know, having certain slopes in the data. It could be multivariate regression, could be different, let's say, models. This is not really very much covered by this tutorial. It goes more into the statistics space. You can consider it's like something like how much media, basically money you put for advertising, and your sales are growing. Some kinds of regression studies to predict a little bit, you know, if you spend so much money, how much you basically get probably in basically more sales. And this could be linear, could be non-linear, so there are different ideas how you can do that. But this is not actually the very much focus in this tutorial here. As I said earlier today, we do a little bit about clustering hands-on and then classification. We prepare ourselves for it today, but do the hands-on tomorrow. Right, so let us start a little bit now with this familiar problem. And is there maybe someone from the botanic field here? Usually we have the mind scientists here from biology or chemistry, or anyone who knows about flowers, botanics? No one. Okay, interesting. In the last tutorial I had in Karlsruhe, there was one, and this interesting fellow, he could even say what petal width and sepal width is, so I was very impressed by that. So let's consider this task of thinking what flower that is. And when I now ask the audience, which I will do, consider yourself the problem we just discussed, classification. There are two kind of classes, definitively, right? Everybody sees that they're different. See some smiles in the eyes. So let's make a poll here. When you think about, you should classify that. Is this an Iris setosa or an Iris virginica? So who thinks it's Iris setosa from the audience? Just one. Okay, two. And the others looked in front of the slides, or no? And who thinks it's an Iris virginica? Okay. Now when I ask why, let's have maybe one voice. So the gentleman here in black.
Actually, I was just trying to help because no one else answers, so I answered.
Very good.
Everyone needs an answer.
Very good. I think we conclude with ourselves, we can't be really sure. Right? I mean, botanic experts and the people that have flowers every day maybe can be exactly saying, well, it's very clear that this is an Iris setosa, right? So, and in a way, we think that's not really the case. And if you be honest, perhaps, some of the domain experts, when they have 50 flowers in a row to classify in the field, they may also want to have some machine learning helping them. So the question is still how we do this, right? So how we can now actually differentiate these two classes. And this is something where we come now more to the attributes. But let us just fix shortly these yellow blocks here. When I do yellow blocks, that usually means something important, right? For my students, that means in the exam very relevant. Here in this case also it reflects the CRISP model. We will talk about it later. But still, it's something what you think about a systematic way of doing data mining that you should, when you go out of this room today, know about how to attach basically to yourself to data mining problem or machine learning problem and do it in a systematic fashion. So we're in the first phase here of really understanding the problem, right? So the problem understanding. What we want to do, classify flowers. Okay, did we know how? Not yet. So let's find it out, how we can do it. So first of all, we say the learning problem that we really have here is we have these two classes, so it's a binary classification problem. So it's a really, really simple problem. At the end of the day, we will motivate that we need much, much more multi-class. But here in the simple example, we have two classes, and we have a new fellow, which was a blue dot, right? We want to classify now. It is a prediction task. We want to predict if that flower is this or that class, right? So when you think about what can help in the data, any idea? Maybe from the audience. Look at the flowers. Okay, the lady in front.
The number of petals of the...
Okay, yeah. Interesting, yeah. And then in the back there was one. Yeah?
Yeah, the colors of the leaves, the area of the leaf surface.
Right, colors of the areas of the leaves, and we have the number of sepals and petals and so on. That exactly is what we're now thinking about, right? We're looking more closer to the thing we really want to classify, which brings us to the point of attributes, right? And here the idea was going into the right direction, not necessarily color though, but the sepal and petal aspects here of this interesting flower, and where I said, so probably only the experts really know what is here, the difference and so on. But for us, it's very nice. We have a machine learning, let's say, data set that is already prepared, giving us this information. So we can learn from a certain amount of classes, basically for the three classes. We will see why we have just two in a minute. But we will have basically three classes here where we know already the sepal length, sepal width of all the samples we have. And this is a very nice data set. And it brings us back to the data understanding phase now, and also of your feasibility of the approach. Right? What I said to you, when you start with a machine learning project, you always go through this 1, 2, 3. So we first ask ourselves, is there a pattern to be detected? Right? And in a way, there seems to be a pattern derived from petal length and petal width. It somehow influences, if you look at all the pictures, they're all a bit different, but they could be matching up to different classes. However, I think you will agree with me, there is no mathematical formula yet of saying precisely at this particular growth factor in this petal length and petal width, we can consider as an iris setosa, otherwise virginica or something. So this is also the second point where we said, yes, okay, there's no mathematical formula. Yes, there is a pattern to be detected. Very nice. Where is the data? And now usually the real work starts. When you look at the data collection, here a very simple one, as I said, from the UCI Machine Learning Repository, just 150 label samples. Very little data in a sense today for big data. Hence, very good for showing you a real example how data analysis in machine learning really works. So we call them data points. Labeled means they have basically class information attached to them. So for every flower image, so to speak, we have seen on the other slide, we know exactly this is this class, it's a label available to us. Now also for us as machine learning, a little bit matters a balanced property. So if you want to learn something out of the data, it's very important that somehow your class representations are very good balanced. It must not be exact, like here, right? You see here 50 samples per class, which means in each of these different iris setosa, vesicular, and virginica, we have 50 samples to study. That's what we know, what are the different flowers, what type they are, and so forth. However, if you now think you want to learn some pattern where you just have two samples, let's say from a very aspect of movie renting, you say like one movie was just rated twice, so it's very hard to do a judgment about that for a user, for another user, right? While another movie was rated, let's say 500 times, then it's much more easier to rate. Is it comedy or action or thrillers, or people like it, like lead actor and so on. So of course this balanced class representation will be among us all the way. And at the end of the day we will come to some of the classification examples where we have highly unbalanced classes and so on, and we will see what we do about it. So this is really the data understanding phase in the CRISP model, where we look into and where it also starts with you. So here and there we do exercises, that's the first one. Everybody should have an account, right, on the machinery in Ghent. Is there someone who has not an account in the moment? Okay, if that's not the case, very brilliant. I switch now from the slides away and encourage you to do basically the same I do. We will look a little bit into the data sets now that are available to us so that you get a little bit of practical feeling what is the ERIS data set and so forth.
For the people who want the slides, I added a link to the website, to the HPC-UGent support and then training. The slides are there, and they're also added to on the file system, so Mort is going to show you where to find it.
Yeah, the first step you have to do is SSH into your machinery with your username and account, right? So it is basically this part. Of course, everybody has a different ID here, right? So that should be clear for those of you who are not so much familiar with SSH. Here you have to enter your own ID, but what the system we use is a login hpc.ugent.be system. So that is something where we enter into the system based on your SSH key you delivered already when you created the account. We are now inside the system. You can control that or check that if you want with hostname -f, for example, which shows you, okay, we're now in a login node here. And interestingly enough, we will see again there are different clusters here. And the one that we are interested in is GoLet in the tutorial. And I'll show you later how to sort the modules and so forth. But that's not relevant in the moment. We want to look at some data. And the data is basically available in this interesting, longer directory, Ghent tutorials, machine learning. If you can just look into that and what's available there. This is CD, you go into the directory.
Mortis?
Yes?
Make it a little bit bigger.
Yeah, okay. Try to do that. Is that better?
Yeah, it's okay. Maybe a bit more.
Okay. Like this one. Everybody can see in the back? Okay, good. Excellent. Right, so again, SSH into the cluster is important. This command, if you missed it because it was a too small font, once you're in, you see, everybody should see this welcome. Everybody see this welcome login? Yeah? If you're not, scream now, because now there's time to check your account, but it doesn't seem to be the case. So everything works, great. If you're there, try to get into this interesting directory, because it will be our directory for the tutorial, right? You will find their data, you will find their models, viewers, and so on, that we will use throughout the tutorial. And they're basically a little bit now different between classification that we will mostly, as I said, tackle tomorrow in practice. So we go today into clustering. And here are the slides, right, that I will upload, or that Kenneth is actually uploading then here in the lectures, so you can see them here. This is the first lecture that we have now. But let us go a little bit, in classification now, and explore this ERIS data set. Right, so we are right now here in this directory. Is it still visible? Okay. So please move in this directory. Here, Ghent tutorials, machine learning classification, ERIS. Right, this is this flower data set we have just seen. It's a real one, so it's not just PowerPoint slides. So let's see what that means when we look a little bit on the files which are there, and here you find the original one that is actually downloaded and scaled and so on. That's not so relevant here in this tutorial right now. What's relevant is that you see I always removed and added some classes in the pre-processing here of this. And this has a particular reason of demonstrating you linear separability versus non-linear separability. because two of the classes will be then basically linearly separable, and that's very nice in machine learning. And then there will be some of them which are not linearly separable. So this is a data set we will then also use a little bit also tomorrow, just to make some certain points. But as it is a very little data set, it doesn't make sense to use a HPC machine really. You can use this one really with MATLAB, and there's no problem with it. So when you want, you can basically get a little bit in one of them using, for instance, head. This is a command that you can use here in order to get a little bit inside view. But here, of course, I leave it to you. If you have your own editor you would like to use, like some of my students use Nano, some others actually prefer VI. I personally also use often VI because it's available on edge of the different HPC systems all the way, while some other editors are not. What you see here is the famous libSVM format. We'll talk about that again tomorrow a little bit more, but you can see a little bit here in the front are the class labels, right? Here the first part in the line are the class labels, so these are all representations of class 1. And then you have here the so-called attributes, or as it is sometimes called, features. The attributes that we have just discussed, now basically in a format that is of course machine understandable, so it's the separ length, separ width, the things we just discussed. So you see also machine learning is a very much a topic working with numbers, right? Even if we have images that you have seen, if you want to classify images basically based on pixels, we would transform the pixels, for instance, to grayscale, to RGB feature vectors. So usually machine learning is often very much using numbers, hence of course because we use lots of mathematical equations and mathematical algorithms, right? So and when you basically see that it's a testing aspect here, right? We have training and testing, that's a topic we will also talk about. You always need these different ones, and in fact we will see towards the end of tomorrow that you should also consider maybe in a practical problem using a validation set. However, in this very simple example, just think about this. And when you look now again, maybe in the others, you can do also more, for instance. Just look a little bit inside the different aspects that you see here. Then you see also with more, for instance, if you look into this data, here you have class representation 1, but here suddenly a break and there's suddenly representations of class 3. So these are the different iris, Setosa, Brasinica, and so forth, just modeled as the label from 1, 2, 3, right? These are the classes 1, 2, 3. Now this is an interesting data set. And as I said, you can play around this in many of the tools. The first step you usually do as a machine learning guy is to understand the data set. So you don't go into each of the different sample and look, okay, this is now 0.5, this is 0.7, this is a 1 point, etc. That's not what I mean. By looking at the data, you would like to first consider maybe metadata that is for some data set already provided. So if you go now and download this from the official website, for instance, you will see there is a metadata file with iris names, for instance. It includes metadata. And this is always the first you should check. So not going into the samples directly of learning, that would be bad. It's called already, bias in learning, and we will not go in this direction. Just look a bit more of understanding it. Here you find information about the creator, and so on, which is of course important when you study the data sets. You should quote those that created the data. But of course interesting for us are these aspects that I said to you already before. We study, okay, there are 150 samples in the data, or instances, or you name it. So each of the different fields had always come up with different, let's say, aspects or different terminology really for the same thing. So they are all instances, samples, they are all basically used interchangeably, meaning the same thing, your data items really. We see, okay, 50 in each of the 3 classes, so we know it's a 3-class problem. We have 50 samples per class, very much balanced, very nice, numeric, and one predictive attribute. You see here, predictive attribute, sometimes called target, also and the class and what I say before to you was just basically the label. Right? Some other call it just label, some other predictive attribute where you see here. That is basically what we find out for the new ones that we will get. Let's say we get new samples which are basically according to these instances or also from the same kind of flower type. You would like to find out whether it's these classes. However, this information now gives us a possibility to learn from the data. Right? So we know about it now, and this is the first step to think about. Now when you look how you work in practice, then you would basically read it in if you want, for instance, in Riedel. That's what many of my students do. And there are some pitfalls. Here you see, for instance, just an example for you. When you go into practice, the header is sometimes considered to be special, right? Sometimes considered to indicate what are the column names. In this example of the iris, that's not the case. However, if you use tools like, I think this here is Riedel, for instance, you get the problem that, sometimes the header is, the real first sample is already a header. And this is something in general, in all the tools that you're looking to, you have to take care and look at these things because they can basically influence also your learning and also basically influence how you look at the data set. So here in this example, you can just say, use the header, right? And say, okay, the header is not there or is there. So that's something what you should always do, not only in Riedel, also in other tools. That is something we consider the data preparation phase, the third phase. Right? Now we look in the data and we prepare it for data analysis. So this firstly means checking metadata, headers, getting better to know the structure of the data. Like, okay, we have here really 4 variables. We have the fifth, which is a label. However, we've seen here already, okay, we have a text label. That's sometimes a bit strange. So sometimes you would then consider in the data analysis that we have seen in the data on your cluster, for instance, you change it to a numeric representation. So 1, 2, 3, for instance, instead of a real text-based label. So this is something what we do beforehand. And there are some, let's say, other terminologies I want to just bring across because they're very, from a practical perspective, very important. So the one thing is, you have seen when you were logging in, somehow there's one class always removed, right? So when you go basically in this direction, as I always said, remove the third class, for instance, that is something we call, in a way, sampling. So we try to get those data that is of interest to us. And this is also a very important topic in machine learning, again, which differentiates also this big data analytics hype from the machine learning which was existing like 20 years ago. So you have to have some purpose when you go to the big data or to the data set you analyze. So just throwing any machine learning on it, or just use all the data, all the feature that are there, or all the samples that are there, is not necessarily the best way to do. And in many cases you will subsample. That is something what you see here. For instance, in our example, as I told you, we were in the beginning just interested in saying, is it the Setosa originator? So we would say we sample here out of these 3 classes, those 2 classes. Right? There's a process called sampling, should be in your mind. It's a very important term when you go to practice. With this, we have a binary classification problem, right? Everybody sees that. We have 3 classes, now we remove 1 class for a specific purpose, I will tell you later. But basically now we have a binary 2-class classification, a very, very simple one that we can actually do with very simple models. Now this is one way of data preparation. The other one is basically maybe all the features, all the information about the data itself is not every time needed. So it depends on your application domain problem, right? So in this example, for instance here, it's enough for us when we have these 2 classes only. So this one we removed, you remember in the last step. But maybe also some of the features, you remember we had 4, all selling these different items. Here's a sepal and petal, means the length. Maybe just the petal information is enough, right? And then we do our model, and we would say simple model better. It's a machine learning philosophy, if you want, or a fundamental aspect called Occam's razor, that you basically have always the most simplest models you can get. So if you think, for instance, that here petal length and petal width is enough, then you keep it to that. And this goes for every data set you touch in the future. Don't necessarily think all the features will help you. If they can disturb the classifier, they're getting more and more noisy, the term we will talk about later. right? So think about this process is also very important when you do machine learning. I know it's fundamental, sometimes the people think it's a little bit boring, and why not use all the big data in the world and then you classify correctly. This really helps not only to save computational time, it's also better for the model understanding, so you will see that this is a really established practice. So you see from 4 attributes here, we basically then select 2. Very interesting. And if you now look on the kind of data that we have again, in part of the exercises, this is of course something you should consider doing. So when we look at some of them, this one for instance. You see here, this is how reflected in the table, right? We said we have changed the label to a numeric representation. Here's, for instance, all of class 2. And these are the attributes you have seen. So 1 attribute, 2 is missing, 3, 4. So why is there 2 missing? Any idea? Yeah, this is something to do with a sparse and dense representation. So this means you save basically time. If this is a value that is not assigned here, for instance feature 2 is 0, then you avoid it to be present, right? You assume that, and this has to do with a specific data format. So that doesn't mean necessarily that it's completely gone, it just says, okay, for your learning, okay, feature 2 is 0, that's why it's disappearing. It's also something you have to think about when you go to a practical problem. The sparse versus dense representation of data, especially now in big data. If you think about Facebook or Twitter, the likes, right, are extremely sparse, right? You have a huge matrix, so to speak, of saying like, and these days they go even to graph representation, who is liking what, right? You can see it's a big matrix of users versus, content material, and then you would have, say, lots of zeros. And it doesn't make sense to have a table storing all zeros and then a couple of likes for those people that like a certain kind of entry. Right? Hence you have, let's say, more sparse representation like this one where you just omit those which are 0 anyway and put those which are basically have some really valuable information for us. However, you see here, again, coming back to the slide content, the 4 attributes where you can work with, but consider really in practice just removing those which you don't need. And this has not to do with the sparse versus dense. This is something to do with your feature that you probably don't need, where you think about for your classification problem, it doesn't matter. Right, just, get a little bit of feeling for working with the data right now, that's the idea. So when you see here in the exercise, we don't create a model right now yet, but still having this feeling of using Unix, CD, and, looking into the data with more and head and tail and so on is quite good to get better at the practicals later on, and to have a real understanding what it means in terms of data sets. However, plotting the data is maybe also a good idea. So let's come back to the slides, continuing a little bit with terminology. So when we think about now plotting this data, this is the actual data you just see, just of a basically 2D representation here, and we have here the petal and the petal length and petal width. This is what we consider now the attributes in a more mathematical formulation, right? And we say the attributes in terms of D, meaning dimension, right? This will be a terminology that stays with that all the tutorial until the complex ones tomorrow. Now everything seems to be very clear, and we put it as a vector, right? In this sense, it's a 2-dimensional vector, say the petal width and petal length for each of the data instances that we have, right? So you see here, the instances are very much, apart from each other, seem to be a pattern, right? As we assume from the picture. So indeed, petal width and petal length seem to be a pattern, that some of them are just, longer, if you want, than others. And so this is something what is interesting for our data set that we study. And if you look at the data set at this point of time, we have like 100 samples now painted here, and these basically mean in a kind of collection of the vectors, we have just, let's say, 100 vectors of 2 dimensions, the mathematical description, right? So This is important, but you remember we had also some interesting thing, class labels. So what is this thing? Class labels, as we talked, and coming back to our initial idea, are already labels that someone was saying, okay, this is a particular type of flower, and this also. So this is something we can learn, saying for each of the two-dimensional vector elements now that we have also a certain label we call y, which is, from 1 to n, which is a number basically of the classes we have. So 1, 2, 3 in our iris example. In this particular one, we have just 2 classes, so basically just 1, 2. And here you have the different types, so we know that already. This is not machine learning so far. Right? It's just painting or actually creating a nice figure showing that. However, for our mathematical description now what we have is we have x, the vectors, and each vector has a nice label. Right? So this is a quite nice thing that we now can use for learning. Right? Now we have basically the prerequisites for supervised learning, and so we use it because we want to find out, can we have here something, right, which actually differentiates these to those flowers. If you have new points, someone measuring in the field, right, going out to the flowers, as is measuring and see, okay, we have now a new flower which tend to be here. It's not exactly perhaps in this ring, but still, is there something which maybe can help us here? And this brings us to the idea of a so-called decision boundary between them. Now, decision boundary is an extremely important term, but take away the method, the way we do it now with one line is a very simple approach. You could have, for instance, tree-based decision boundaries, which are perhaps something like this, now very much blocky, or you could have a line, right, linear model that we will talk about today. Others would maybe consider a parabola or some certain degree, polynomial to some degree. So these decision boundary in 2D could be many parts. And then if we go tomorrow to multidimensional aspects, we will see it's actually a plane, right? So a surface really of differentiating different parts of it. But I think you will agree with me, we can find there something of saying perhaps here, if we have a line there, and we can establish that now and learn from the data here and there to create this line, then we could say, okay, the blue one tends to be much more, here's the iris setosa on the left hand. And this is exactly what machine learning is doing. It is creating systematically this line. However, it's not exactly function approximation. So some people know perhaps function approximation. It's a topic which is very similar. However, here we learn from the existing example to be good for the generalization, so for saying out of sample is most important. This is in sample, these two, this is out of sample, we want to be good for that. So this is something where, this is machine learning where we want to talk about. So how we create a line, I think the most of you will know that mathematically. Just go quickly about through this, how we create this decision boundary. If you think about now this line as a threshold, you could think about that everything which is, across or bigger than a certain threshold should be this iris virginica, and if it's below some certain threshold, it is basically the iris setosa. So that is how you create the first, let's say, towards the first learning model, the perceptron, the idea of separating something with a line. So this is basically something where we consider what we have here, and if you look closely, what we have already is x, I, right? These are constants for us. Why they are constants? It's our data set, right? The x's are already given to us. That's where we learn from. And we have our guiding input y. So the only thing actually what we need to learn in order to get this interesting line, if you know a little bit about mathematics and the line function, right, are the weights, the coefficients of that line. And we sum that up with our different, let's say, dimension that we have in the data set. This is this interesting formula. We kind of use a threshold here, and it's a little bit a compactor notation as this particular part, right? So this brings us then to put it in a sign of saying, when it's +1, it's perhaps this class, and -1, then it's the other class. That's a more compact notation. As an example how that works out in practice, here you see different weights, different x's. You basically then have this decision boundary, and of course, if you equal it like 0, you are on the decision boundary, and then it depends on your mood, right? If you're a credit card approval guy, then you don't have really, you do use your gut feeling. But normally you would be in a space like that, or like that. So hence, it is really a decision space that this linear decision boundary is creating. And every new item, these are the in-sample ones we know already, but every new item landing there will be kind of considered of this class or the other class. Right? And this is, for instance, also a very good book, if you want to. I use it often, also very nice R examples, because I have seen some where people already using R. This is a very nice book to study. But let us come back now. We know the line is not everything, we have a decision space, and we will come back to this in the formal way in lecture 3. However, now let's stick to the very simple learning algorithm you can find. And this is the Perceptron learning model. As I said earlier, interestingly enough, it's basically in the late 50s developed. Still very, very relevant today, as you know that neural networks, in a sense, it's a key building block of neural networks and also of deep learning, this perceptron. So we want to model this, and if you model this now, the idea is derived from this model. You have different x's in our input, right? That's our data set, our constants that we have. And on the other side, you basically have the y's. That is our label that we also have, right? So that's something now where we think about, okay, we kind of having an activation function in the middle. We sum up this and put it here basically to the simple sign function in this particular example of saying it's a +1 or -1 depending on the sum of this minus the threshold. So this is a derivation basically, and you can scale here with the number of dimensions. So it's not only for 2D, you can use it for more dimensional data sets here. However, it's an important property that needs to be there, and this is linearly separable. Right, so this is really the kind of key idea, and with the weights now that you learn, these red things, you steer the line, of course, but also think about a different view, the strength of the signal. And the strength of the signal means, depending on which features you have here coming in, right, they also get different weights. So for some of them, the weight is very important. Credit card approval, a very famous one is, for instance, your years in residence, right? If you tend to be living 10 years, at some point this weight becomes very important. While you have to know other kind of features or other kind of part of the credit card approval process might not be so important. Like age, young people get credit, older people get credit, but if you are living in some certain place, however, for 20 years or 10 years, then of course this weight seems to be important for credit card approval. So basically what this algorithm is doing, learning from this data, adjusting to the weights, according to this pattern that seems to be important to the data. Right? It's not perhaps perfectly obvious to you, we will see how that materializes in the next lectures, also when we talk more about the subject. So this is the simplest learning algorithm. Here's an example if you want, a very trivial example if you want to play it through. You see here, this is a data set that is basically given to us, and overtraining this data with the perceptron learning algorithm that we will have in a minute, we come to these weights. And now if you put these weights in the typical equation that we basically just seen here, so you basically have all your x's here, given here. Here's the sample 3 that we take, for instance, for an example, where we then have the weights, multiplied by the values that we get from the x's, and actually, in fact, it's bigger than 0. So the class representation in sample 3 is 1. Right? And then the counterexample, which is here sample 6, we pick this one, where we say, okay, we multiply these x's here, put that in the weight formula that we learned, and come out to a value which is smaller than 0. Right? Also, this is something where, very simple, but it explained this sign function. Right? With a sign, you just say +1, -1, and you then have already done basically a classification. Now, you don't want to summarize this. This is something what the perceptron learning model and the algorithm is doing for you. So still the question is how we get to these. Right? Now, this is something where you can sit down and maybe try out manually, long time. But of course, we want to do and automate the process using machine learning. So this is something which brings us now to the idea of a so-called hypothesis set. And this will be a notion that we will take care also on throughout the whole lecture series when we talk about h of x. So the hypothesis basically that we have here can be very different depending on the learned parameters here, right? So you would see that is a hypothesis for our problem, but also this is a hypothesis for our problem, right? And you think about every line that you can have now, differentiating these 2 points will be different hypotheses that we have. And this is important now for the theory of learning that I will bring across in the afternoon, that you can come up to the idea there would be actually maybe infinite number of lines. So how we pick the one that is most important to us is of course a key question, right? And for this we need an algorithm to say, now it's good enough, that's the line we want to have, and we stop here. Alright, okay. So here we have the summary of the perceptron, and this is a little bit related to different hypotheses, because when we see a line here between the different 2 classes, we can find any line, right? And this is now the key message. We play around with the weights, which means we're adjusting the line, also the threshold, of course. So we play around with this line as long as we find something which is differentiating here, the 2 ones. However, both of them are a hypothesis for us and say, okay, this could be a valid line and this could be a valid line. And now when you a little bit look ahead at what will come in lecture 3 and so on and 4 tomorrow, and this is actually the topic where then also SVMs take place. They find the best line out of many lines. And this is interesting stuff, and tutorial we will do tomorrow. However, for the perceptron, the very simple model, we are just happy with any line that is separating these 2 data sets. However, we can from our gut feeling already know that perhaps this hypothesis seems to be much better. Why you would think that way? Anyone has an idea why you think it's better to have perhaps this line instead of this one? Yeah, there's one on the back.
Because in the left example, the line is too close to the blue feature, to the blue labels. So it's better to make the distance between the line and the labels bigger.
Right, so the answer was, it is the line on the left is indeed too close to the blue point, right? It's in a way furthest away, basically from the samples would give perhaps the best line, because we always assume there will be a new point coming, right? A new point coming that we want to classify now. And now if you think about a little bit how they are aligned here, these dots, think about, you know, the likelihood that there will be a green point will be okay here, but the likelihood that there could be a blue point could be essentially already here, and then it would be misclassified. So we aim for a line that is, you know, furthest away in a way from the points, but that's not what the perceptron can do. For that, we need support vector machines that will follow tomorrow, right? So this is interesting. Then there's lots of playing ground, if you want, with these fundamentals, just with one line separating the 2. So coming a bit to the notation, also already, let's say, as a kind of terminology fix for the support vector machines later on as well. These are things which are in the literature often very much different. So some of them use W transpose X, which, if you remember a little bit about mathematics, is nothing else than putting the vector that you would have otherwise in this direction, you put as a column vector here, in order to multiply it then step by step with, you know, our data set. With our X that was constant, if you remember. This is of course the data that has been given to us and the weights we're going to learn. And actually this is equivalent to the dot product. This is a very important notion we will see tomorrow, will be substantially be a key part of support vector machines and understanding their derivation. So again, from the simple perceptron, then we can do, let's say, a more compact notation. The following, if you remember, the threshold was here that we have done, that is also a learned entity. And if you think we learn it anyway, we can see it as a kind of special weight, right? We learn from the data. So let's put it as a special weight plus W0 here and put that as a threshold. And our data that we don't have for this threshold really, right? We kind of always assume 1. It's a kind of small trick, and you see here the notation starts now with the x0, so to speak, the summation, just to come to a much more, let's say, compact notation of all of this, right? So that you have this dot product between W of x. It's nothing else that you see here on the left-hand side, but which is much more compact in the dot product notation. So if you don't know using machine learning books, you find sometimes these notations with W transpose x, the dot product, And the original Perceptron was really this, but it's all equivalent, right? So this is just, let's say, simple math. And the interesting takeaway message for us now is the dot product here, also when you think about machine learning and support vector machines tomorrow, it is a scalar, right? So when you do this dot product, it is actually something, a real value. And this will be handy in many cases. For instance, of course, also for our aspect of the perceptron, it's a +1 or -1. If you remember, as a negative or positive, and we put it in the sign, which means then we get the sign as this class or that class. But we will also see tomorrow that it has interesting properties in the support vector machine when we talk about the projection capabilities that basically this dot product has. That is a little bit explained in this interesting formula, but we can actually see it as a projection when you have the dot product between U and V here as a projection of some line going this way. I stop here because then, that would be more material we take off tomorrow in the support vector machines. But this is an interesting aspect that is, of course, again related when you think about more sophisticated models than just the perceptron. So what we didn't know still is how we get to the W's, right? So we said we have no interesting notations, a compact notation is W transpose X. So how we get to the W's we want. And this is here the algorithm learning steps basically. And you see it's an extremely simple algorithm, just having, 2 steps really of saying we pick any point we like, which is misclassified, and we want to make it better. And we put it in the formula. As you know, we have that already in our compact notation now, and it will give us out -1 or +1. And if we have the label set as -1 or +1, it will either be correct or incorrect, right? And then this is something what we just update then, this kind of misclassified point where this is actually true. Then we basically update this weight vector with just, having this kind of label that you have. In other words, if you think about now what it means in terms of vectors, you're kind of switching this, let's say I have also a video later on, with adding or subtracting a vector, right? So everybody can see that perhaps better on the right hand, right? When we have the kind of first case, we add a vector if it's +1, or we subtract a vector if you have here the visual representation. And with this, we change fundamentally the kind of order of the line. And now the interesting thing is you do that again and again and again and again and again. And you go your coffee, you drink your coffee, you let the machine do the work. And then at the end, it will be actually converge. And that's the interesting property that was already found in the 50s. A perceptron learning algorithm converges if you just do that many, many times. However, there's just one side remark. If basically there's linearly separable data, so we have to talk about this separability a bit. Yet I want to show you a short video how this perceptron learning algorithm works. Usually in my lectures I get very good results, kind of feedback from my students that they like to have some videos in the lectures. And here you a little bit can see how that actually works, right? So the perceptron learning algorithm is going through all the misclassified samples, goes over and over and over, and at some point in time, it really stops and says there's no misclassified point anymore. It is very hectic in the beginning, and could be actually hectic all the time. But you see here this one property of saying linear separable. Somehow these two classes that you can do a line is a very important aspect to let it converge. Otherwise, it will be never converge, and will be, it will be going in cycles all the time. Right. There's a little bit an idea of an exercise which I skip here a little bit because of the time, and then we continue with the second part. But there's a question here in front. Yeah.
How can you know a priori that you can separate your data?
It's a very good question. So the question was for the online audience. How can you know before that there's linearly separable data, right? So this is actually, in practice, you do not. It's a simple answer. So really, when you go to practice, most of the data sets are non-linearly separable. It's more an assumption here to show you the simplest learning model possible. And hence we will talk also about more tomorrow support vector machines, aspects of allowing error, which help actually in thinking about linearly separable and non-linearly separable data. said, so this is something we evolve to, right? So no worries, we don't stay with a simple assumption. This is right, you find that rarely in practice, and the way to find out is also, of course, either you do a figure of the data like we did, and we can see, okay, it's linear and separable, or you make a script that is checking some averages or so. But in practice, really, in most cases, it will be not really linearly separable. However, for the point here of the simple learning algorithm, it's still an important property that you actually can and basically should look at just to understand the kind of aspects better. So the second part of the lecture should be a little bit more having a broader scope. So what we did at the beginning was we have our first learning algorithm, and we have seen it's essentially lots of math, of computing to get the weights right? So what you see there is lots of vectors being multiplied with other vectors just to get the weights right and changing the weights over time iteratively. So iteration will be an important concept of many of the machine learning algorithms. So what we talked about in the beginning of the lecture was also the systematic process. I don't want to take very much time with it because it's a very theoretical substance. I put you in the slides an appendix on it, right? So you can see all the different steps with all the sub-steps, and you see it's a very big kind of model that you can use. However, in practice, in industry, it's quite used. It also comes from industry, and it helps really to structure a little bit the process. We had already problem understanding, data preparation, if you remember all these steps we have been going through with the IRIS dataset. And here is really in the modeling and evaluation where the learning takes place. This is really machine learning in this part. Now, which different models you have? Is it a perceptron? Do you use support vector machines, artificial neural networks? That's the modeling. And the evaluation we will talk on in the second part now is really, how do I know that my model is good? So accuracy, error rates, and so forth. And the sixth one is really, if you've done everything right, let's say your prediction for the stock market, there's a time series model, right, is right in your in sample, and you have a good model that hopefully predicts the out of sample very well, it's ready to be deployed, you go to the bank and have the deployment step. So they put it in their bank somewhere down in the cellar, have the model running every day, that is a deployment step, so it's ready for practice. However, before you go there, we have to really make sure that you don't overfit the data. There are lots of, let's say, technicalities in machine learning which is not so simple. And we will talk about this toward the end of today and also tomorrow, when we basically have things like regularization, validation, that both prevent overfitting. So in the moment it looks all like, we have a simple line with a perceptron and a little bit of data, let's the weight do the work and we're done. Machine learning is not that simple, right? And we will learn in the next couple of lectures why. Just this lecture, like the linear separability assumption, are just for getting you the very simplest model possible. Right, in terms of machine learning in general, we should say, and in data mining as well, there are kind of these two tasks. So depending really on the application domain or on your kind of task you get, what type of task you have. The predictive task is very much known today, where we want to have now basically the species of the flower, Iris setosa, that's the example we already had, or we want to basically do predictions. What would the viewer like in terms of movies? The Netflix example, when you rent movies, for instance, or you basically have predictive maintenance, right? You have, let's say, a wind wheel. You want to know when it's most likely to kind of break down, and before some of the, let's say, parts will stop, you want to do the repair before, proactively. So you kind of predict when there would be the maintenance required. In order to save time, you probably pre-order all the materials you need a helicopter to get the team deployed on top and so on. This is a very huge topic today in industry, predictive maintenance. So basically out of your history from all the wind wheels, you would analyze the data and know a little bit these certain parts of the wind wheel will fail according to this in this time span. It's a very practically applied assumption. However, if you think about descriptive tasks, a little bit different. That is where you want to understand your data better. A good idea is often kind of classifying patients, looking more on the patients to understand, when you think in medicine, what types of symptoms you have in the data. So you have much more, correlations, kind of a trend. Is he actually going to some more worse part and needs to go to the intensive care unit, for instance? Or do we kind of, have some certain anomalies in his kind of blood samples? So all of this is a little bit not really predicting something, but it's more describing the patients in order to do something. Of course, then you get a prescription, which is, different from prediction. So that's basically then something which is interesting, for instance, in medicine or also in credit card fraud detection. When you see already something happened, right, and you want to describe what happened, suddenly 17,000 euros for some office material on a credit card, while you usually have a normal consumption, suddenly a peak. That's quite unusual. That's what actually the credit card companies do, right? They analyze daily your usage, and if they see your card was misused, you actually get a call. Happened to me once actually at a conference in Canada that I would cost 20,000 for office material. Someone used my credit card for that. So then I got a call if I really done that, and of course I say no, and then they kind of get the transaction removed. So you see, it's a very applied topic everywhere, this machine learning, but it really depends on the task given at hand, and that is the key message I want to leave here on the table for you. Of course, this is a very simple example with flowers, but you can go on and on into practice like the wind wheels or medicine, particularly, where the features are not that simple like here. You don't have two dimensionals, right? In the medicine, you have high-dimensional data and so forth. This is just really to showing you what we mean in terms of modeling. When we're modeling something as machine learning, we talk usually of having some hypothesis, some model for the data created. Could be a simple line as this, could be a support vector machine, a neural network trained, being ready. That's what we call the modeling phase. And this brings us also a little bit to some things actually also in the break, where already some discussions around it. What types of learning are there, right? And this is something we discuss now a little bit in the remaining, but we will come more to supervised aspects tomorrow. However, what we learned already, in a sense, was the supervised learning, right? So we had the different flower types, we had a label to it, saying, okay, which type of flower that is. So it was supervised, someone giving us basically the labels. We see in lecture 2, after lunch, that we are doing unsupervised learning as well. So what does it mean? We have, remembered a little bit at the beginning, the clustering. So we have some property in the data, like similarity measures or distance, that helps us a little bit to have a, let's say, better representation of the data. A higher level, right? It's just not points, they're clusters of points that we then in turn can maybe put as classes and then do supervised classification or supervised learning. So you see, it's also not something where you see you do either this or that. As a machine learning guy, you are orthogonal to this. You would say, I need maybe perhaps a little bit more better features. I do unsupervised aspects and combine them with supervised learning. So this will be getting obvious today and also basically tomorrow, but most notably also in the next tutorial next week when we talk about deep learning. However, let's stick to these two examples. The third one here is something which I don't really focus on in this tutorial. It's mostly actually known from gaming. So the backgammon, the best, I think, backgammon player in the world is a kind of neural network that learned a little bit with reinforcement learning and so on. So it's really something what you know was always getting some kind of helping input, but not really a concrete label, right? It's more grading of the input. So we talk about these three just briefly, just to understand what we mean now with these different fields. It's very important if you go out of a machine learning seminar to differentiate those. What it mathematically means is nothing else that we discussed before. We have basically our data set, we have the labels assigned to each of the different data set samples, which means we have our vectors, which each of them having a label, supervised, right? That's where the name comes from. So you have in a way correct output you can learn from. This is very nice for support vector machines for the Perceptron now, to differentiate and converge them is the line we're talking about. So nothing new. This was the example we already have, right? So in the unsupervised, we have no output, right? So we learn only with our data at hand. There's no one that, as we discussed in the break, was giving the pixel or the labels, or was really going into the field in the city of Rome of saying this is water, this is a tram, this is a building. So this is missing in a sense, and many of the scientific data sets are that way. and also in industry. And the reason is that labeling data costs usually hell a lot of time or money, right? If you think about the data set that we'll have later with the satellites, the satellite is creating the images, right? But we still have no idea what the labels are. For the labels, we need a team of 10 going into the city, and they have to do lots of manual, time-consuming work of doing, field campaigns of labeling data. So hence, the majority of the data is unfortunately this way, unsupervised structures where you learn from data with no really guiding output. However, as we said, it's not so hopeless. In clustering, we can find, for instance, distinct groups or other patterns that are in this data. However, as this is unsupervised, we can always think like, if there is a possibility to go supervised in your domain problem, go the supervised way, it will be always better. Meaning, if you have domain experts that can give you some labels, it's perhaps sometimes good to invest the time to talk with them. This was really a water mixing event between different fjords. This was basically really kind of credit card fraud to get some labels, right? To get these labels is very, very important. Only if you don't really have any chance, then you of course go for unsupervised learning. Why is it a kind of interesting approach? You see here, for instance, a kind of brain slice that we analyze in Jülich, in my center, and it has different cortical layers that you guys see here in the different, colors. It's a very practical example, right? And the idea of actually getting to these colors is just looking closer into the cells, because you see here the cell distribution is different between the different cortical layers in the brain that have different functions. So it's something no one says to you, this is one layer, this is another, this is another. It's something you find out by analyzing in detail, which is basically this fellow here. In detail, okay, how many of these cells are actually together in a dense fashion, right? Hence, it's an unsupervised learning problem. No one telling me that these are different cortical layers. We just have the expert knowledge of saying, when we look as a human, and actually they have different distributions here. So this is an interesting aspect. However, there will be some regions in the brain here and there where it will be like this. And this is now the typical pitfall you run to in terms of unsupervised learning or clustering, for instance. You see here it's very clear, right? They have kind of linear separability again. But when you come to practice, often you would have these ambiguities. So you don't really have a concrete way of saying where does the new cluster end, where does the other cluster stops, and so forth. Right? Just an example of how challenging really the data sets are. If you go unsupervised, you of course have your very fancy problems where the situation is not like our toy examples we have here in the beginning for getting across a message of machine learning. That brings us a little bit to the third part, basically, that we have in learning. And we do unsupervised learning all in lecture 2 after the lunch, so there will be more details, and supervised learning then tomorrow and towards the end of today. I left out reinforcement learning because it's another really big field. And it's not uninteresting, that's not what I'm saying, but still it needs a whole complete tutorial. The way you can say is basically you have the same thing like, unsupervised. You have not a concrete output. However, you have a grading of the output. So in backgammon, that would be how good was that move compared to the millions of other moves maybe that you and the other one has done in the past, in the previous time steps, and that your opponent was basically doing. Right? This is an example. Or a very famous example in many, many books is always a toddler example. If you have a baby, or as we humans are learning. So when you have a cup of coffee as a toddler, you just go there and say, interesting, ouch. Right? You hit the coffee, hot. It's actually not good to touch. But then you do the iterations, right? You come back, okay, the smoke is gone, touch, still warm, ouch. That's a grading, okay, it's not hot anymore, it's a little bit less temperature. So that is a grading we're talking about. There is some guiding output, but it's not very clear of saying, after 3.4 seconds, this coffee you can touch or drink. Right? It's a grading, so we kind of try that out. And then after some time of iterations, the baby will see, okay, absolutely no smoke standing for 3 minutes, then I can touch it and it doesn't hurt anymore. So this is a grading output in reinforcement learning, and learning from this experience is a key ingredient why it's so good in gaming. right? Because basically, if you think about games, it's nothing else. The experience that you have, and of course, when you can do that in an automated fashion, you're beating also often the humans because you take into account all the possibilities. While even very successful players that are working, and playing a long time, they have basically no chance against the automated approach. We saw that also now in the new deep learning field with the alpha and so on, but this is something that we have in another tutorial I will talk about. And of course the machinery is, in this sense, stronger. Right, so this brought us lots of terminology, so let's maybe make a short kind of conclusion here. So first of all we said, in a way what we want is to get a function right? Somehow we want to get towards a function that explains me a certain function was creating my data, then I get my y. We had the example of the linear function, right? This, having just a line. Then we had data. Here's it very nice, we had supervised, right? Labels always with our input data. That's very important. However, a very important thing that we want to achieve in machine learning, which is differentiates us from some of the regression studies or something in statistics, for instance, is we want to be working well out of sample. We want to classify future point rights. Right? This is a key aspect. Otherwise, it would be rather memorizing. We want to learn in order to generalize well in the future. And this is a key assumption in machine learning. It will be much more concrete when we formalize this. Basically in lecture 3 later, after we have been coming to some of the practical aspects of the topics here. Then when we are in the modeling phase and the evaluation phase, we left a little bit a thing out, which is actually the training set and the test set. You already have seen that by logging in to the system, right? We have a training and testing. There are always these two data sets we're talking about in machine learning. And we will see towards the end in the tutorial, we will have even validation sets to talk about. But let's keep it here simple and start first with the training set. That is basically that you use in order to create your model, right? This is in the modeling phase, but you need something to check if, in case there comes new data, unseen data, you don't know yet. Is my model working well? So what you would do rather is putting the test set and throw it in the corner, I say to my students, right? You don't touch it, only for evaluation. So this would be the same structure. You would have even labels with it. So you have guiding input, but you don't lose it for learning. You throw it in the corner, you don't use it, only once you have all the training done. And we will see that this is not an easy task. There are lots of parameters, right, to be chosen correctly. The Perceptron was very nice because it finds the weights basically automatically. But we will see later on in my support vector machines and tomorrow that actually this fellow here is loaded. And there could be lots of pitfalls for machine learners beginners just using training and testing and reporting a very high accuracy. But in practice, they have used the training set for model selection, which makes a contamination of the data set. So you cannot use that anymore really for reliable estimates in practice. Hence, there's a cure for it called cross-validation and so on we will talk about tomorrow. But this is an important aspect. So every time you face data, you will be basically having this part of the question that you see basically best explained here. You get a data set, and the first thing you do is you put and cut the data and put it in different, let's say, corners, visually, of course, right? But however, this is usually the question, right? Where to cut? This is a very interesting question, and this is something where, again, now mathematics are not to the rescue. This is something which is a rule of thumb, which is often an application domain question. Of course, if you're swimming in data, if you have had lots of data available, I could recommend this, for instance. Use just 10% for training, 90% for test. Then you should be relatively sure that when you deploy your model in practice, it will really work. That means you train on this, create your model, and you verify it on 90% of the data, which means it would be probably a very, very good, reliable estimate. However, if you're not swimming in data, you will see that this 10% could be too less to train. And this is something where now the theory comes in handy, which we have in lecture 3. We need a certain amount of samples to get our, let's say, overall machine learning, just going back to the theory of generalization and statistical learning theory, to get that going. So you cannot just simply do this rule of thumb, because if you have too little data, this 10% training would be not good enough to get your training right. So you see here is again a thing where we have to think about where we actually get the error now when we train down and how we can validate here on the test set. This will become all, let's say, more obvious when we then really go into the theory. Right, so this is important for you, again, when you are in this modeling phase and so on, and data preparation, finish that with training and test sets. And then we have also the question now, okay, now I have this test set, right? I have it in the corner, I have done my modeling. So all of that is, let's say, now done. We have trained the model, we have done all the iterations in the Perceptron, we have our model, and now we look in the corner and we get our data back, which was unseen so far, not used for any decisions in the modeling, just now used for testing. So how we basically say how the model is valid, or basically how it is good. You can here see confusion matrix, for instance, that you use of just simply counting, in a sense, the predicted class where you think your model was in line with your data. And as we have labeled outputs, that is what we can always do, right? We just count the misclassification and classifications and put that, let's say, in this interesting matrix that you see here. Very simple, basically. And this will be then kind of the performance metrics you use for different aspects. And these are usually domain-specific, depending on what is more important. Is the accuracy more important, or is the dominance of error that you want to basically bring across when you talk to your guys in the applications? And you use basically the values that you have on this table of putting this, for instance, in the so-called accuracy term, which is the number of correct predictions just divided by the total number, so the ratio of your correct predictions. But if you, let's say, have something where the error rate is much more substantial, you would basically report that. So usually these error rates are very much used in kind of security aspects. So when it's really needs to be, 2.0, no errors or so. When you go, for instance, excess of some certain critical buildings, these kind of there, you would rather report the error rates. While we will see in our, land cover classifications following tomorrow, we will report the accuracy. It's not so harmful, if we do something wrong. It's rather for us interesting to get the accuracy right. However, if you see here, they are just, let's say, the coin from one side or the other. However, it matters for some of the applications domains to rather report the error rate in terms of, or basically also the accuracy. Now, when all of this is nice, so if you think about you have a credit card approval system now created for a bank, and you get 20% right of your unseen data and testing. Who would think we give it to the bank? Okay, no one. Good idea. So now, basically, I have created my model, and I have 99% right and give it to the bank. Who would give that to the bank? Okay, sure? Not so sure, because if you hear 99%, that will be something alarm bells. Machine learning usually has not 99%. Right? Deep learning models here and there on small image data sets can achieve that now, but usually you would say that's too high. Alarm bells. So even if I do my training well and I use my test set and I suddenly get 99%, I should be careful. Right? And this is a topic we call, for instance, overfitting, where we probably have done our learning too well. And this is a process called overfitting that we will also learn about. Now, we'll see exercises, again, in terms of the time, we have lunchtime now, two times. I skipped that, it was just a small exercise. More interesting for you, maybe before we go to lunch, and then really have hands-on in the lecture too, right? It will be a different lecture very practically, where we use, clustering. Here, just another, pointer for you as a short video, how really real data sets differ from what I was talking about, basically here in terms of the kind of simplicity of the data, right? We had flowers to classify, right? So this is, of course, not something where you think as a normal practitioner you would have your hands on. But here's a very interesting thing in the earth sciences where you can grasp a little bit the idea how real data sets look like. And it's a very nice overview.
Integration. Research infrastructure integration.
Data integration.
Services integration.
So what is EPOS? EPOS is a long-term integration plan. Earth science research allows the understanding of the physical processes controlling earthquakes, volcanic eruptions, unrest episodes, and tsunamis. EPOS is integrating with existing research infrastructures and facilities. The key challenge is to open up the enormous wealth of available multidisciplinary data and promote cross-disciplinary science serving society.
This is important because it is bringing together lots of data and information from across Europe on many different solid earth disciplines.
RIDE is a database system within EPOS in which we have collected all the information to date to form an inventory of the needs of EPOS. The EPOS idea requires supporting by an E infrastructure. A key component of the E infrastructure is the metadata. Metadata is used in several different ways, and we have designed an architecture for metadata that has 3 clearly differentiated levels. We can integrate together different kinds of data sets and different kinds of software with the computer processing available to provide services to the end users of EPOS.
We take the example of the last eruption in Iceland at Jülich. We have seen the economic consequences of this event where the entire air traffic was completely disrupted. Infrastructure like EPOS can really make a difference in this case, in the sense that we are able to analyze and understand the upcoming processes before a volcanic eruption.
The aviation industry definitely is interested because our networks are monitoring the activity of the volcanoes before an eruption started.
The Arctic area and the northern areas have a special dimension. It is because of important natural resources and their exploration, exploitation, and management.
Will enable a step change in multidisciplinary scientific research and public outreach for earth sciences. EPOS supports the European Commission plans responding to the global challenge of data infrastructure and new services to science.
I think we can stop here, lots of important people. But the key message to take away really with this video was infrastructure, services. There's lots of things where machine learners rely on, right? And this is something where we also will see basically in the next lecture. We need a good parallel file system or file system, large storages to have all our data stored, which is commonly overlooked, right? We have the HPC infrastructure, which it makes us possible to analyze the data. So all of this is very important if you think about without data we cannot do anything. And this is of course a key essential thing that when you also think about the metadata we discussed, where machine learners today are not very much interested in analyzing one data set. Right? So this is, let's say, done in the past. Now we have infrastructures in place where we can correlate many of these. So we do data fusion, We do different measurements from different, measurement devices together, and then analyze the data and looking for that. And this is very interesting areas called data fusion, which is a little bit this also alluding to, right? So this is not where you even think about, okay, we're interested in the flower or separating this flower with the other flower. We would be interested in rather saying in this particular area it's growing, and we have this data, we have another data set saying also, okay, when it continues to be in the next 50 years, how it influences maybe CO2, right, when you think of flowers. So we have a completely different research question combined with this. And so this is basically how the practice works today. And also if you go to industry, more and more these data fusion aspects also come into play. People use unstructured data from emails, right? There are lots of emails with customers they learn from, very unstructured text basically. They correlate this with your customer database where everything is very much structured in SQL-like structure, having everything data together, and use both of these informations to create a model of you. Are you a good customer, bad customer? Lots of recommendations, lots of complaints versus you buying a lot, or what type of clusters you belong to, good customers, bad customers. It goes towards the direction that even people use them in terms of classification. They put you in a box, right? And these boxes are typically not good and bad customer. They are different levels of customers. Hence, you see the infrastructure behind it and services is also very important when we talk about machine learning. Right, so this was really the key message I hope I brought across in this video. And of course, everything I talk about and all the different lecture aspects are basically in the appendix here in the bibliography, and I encourage you to look at some of those. As I said, Pangaea, for instance, is an example, or EPOS, you have seen the infrastructure, and also data sets. In the appendix for you at home to study, I don't want to elaborate largely on this. You will see that the structured process, if you're new in the field, it really makes sense to look at them, right? To maybe not overlook some of the things. So if you go there, in the appendix you find for each of the different steps we discussed in the CRISP kind of model that you have, all the different subscapes. Now they're talking a lot of reports. That's actually one of the critics to the model. Don't take it literally, right? So don't every time make a big text written report, but maybe make a Google Docs as we do sometimes, just structure it roughly according to the systematic process and put some findings there. It helps you later on of not repeating the same studies again, and you maybe don't remember it because it's 4 months ago, or basically you know why you picked the model parameter this and that way. So it could help you in there to report some things, but don't see it in a formalized way. Also, when you think about the first, just to come back to this, a problem understanding is what I put there. Of course, the official model says business understanding because it's a business model, but still it flies also very good in science and engineering problems. And then data preparation, all the different pathways are very nice, different tasks where you directly can see how they reflect basically in machine learning models. Also, when you think now about evaluation, think about that this model is not a waterfall model, as we call it, right? It's not 1, 2, 3, 4, 5 done, or 6 done, right? Usually you always go back. You evaluate and see, but my accuracy is not good enough on these 2 features. Consider the Iris case. We have said, okay, maybe 2 features will work. So we worked on it and see the accuracy is very bad. So maybe we have to go back and add the 2 features again. So hence we are in the first beginning of the CRISP steps, adding again 2 features. The PETA is not enough. We maybe also need the ZEPA. So then we add this and go the whole process again. We create another model with 4 features now, and then evaluate again and see, okay, the accuracy is much better. Now we can basically go to the deployment phase, use the model for practice for new unseen data, right? And then it could be even typically in practice that after a year or 2 you have it outside in the field, the people come with new ideas or features and say, oh, we have learned that customers tend to do this and that. One example is now, compared to, for instance, 10 years ago, now you can track exactly on the website, where are you, right? How long time you spend on which pages, where you click exactly where you tend to be. They use this information, it's all tracked, basically what you're doing on the website, for customers that buy, and then put that as a feature So they know exactly which other products you're interested in. Not the only one you bought, also the one you looked at long, and stuff like this. Just like practical examples in industry, how they use this, and this is incorporated then again in the model. So this is, let's say, again, the cyclic aspect of CRISP, but then also consider that one model might be not good or maybe not enough for it. So I was recently at a company, industry, they do interesting, let's say, biofruit and medicaments for, let's say, more the older generation of people. And when I was there, I talked to the machine learner there, and they had 125 models working all day. They don't have any kind of company store, right? It's Dr. Hittich, if you want to be interested. If you look on the website, Dr. Hittich, they have lots of pills for, lots of pains everywhere in the body. But interestingly enough, they're making not a very good revenue, plus they have no store, no physical store, only online, right? And they make huge revenues. They don't have the cost of, like Douglas and everyone else of having these stores somewhere, and apotheques and so on. They make everything online, and the key to their success is machine learning. And why? They have 125 models in parallel all the time, running over all the data and know exactly each customer very well. So they do predictive flyers, knowing exactly then when the customers seem to require a new kind of box, because now we know from the time measurement, okay, the pill box would be empty, it's most likely that he comes back. And all of these kind of things, where simple models will do, combined with more interesting models like, will he be a core customer, or just a customer that loses interest. So you see that has lots of practical aspects, and also it's not the front of the company you mostly will not know, right? So when you come there, for instance, it took a long time to actually talk to this person. You have to dig through usually in industry to get to those people that do the machine learning models. They're somewhere in the cellar just looking at the data, but are very good in understanding the data and modeling. Right, so this is a little bit, practical views, but before we go to the lunch, we probably have also some questions from the audience before I talk here so much, because we really concluded lecture 1. I hope everybody is a little bit now familiar with machine learning, what it tries to achieve, the basics. Admittedly, a bit less hands-on, but this will come now lecture 2 after lunch, so get your hands warmed up in the lunch. Any question? You can ask anything, don't be shy. Okay. Yeah, well, going once, twice. If that's not the case, let's break for half an hour, or? Yeah. So half an hour we'll be back here, and enjoy the lunch. Thank you.